Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. Look, if you've been paying any attention at all to the tech world recently, you know we are right in the middle of a massive, high-stakes battle for the future of computing. On one side, we've got the traditional heavyweight champion, x86, and on the other, the incredibly agile, wildly efficient challenger, ARM. Today, we're going to break down exactly how these two completely different architectures work, why they're fighting for dominance in everything from the laptop sitting on your desk to the world's largest data centers, and what all of this means for the future of the devices you use every single day. So here's our quick roadmap for today's showdown. We'll meet the titans, break down the foundational RISC versus CISC architectures, explore this new energy efficiency revolution, weigh the server battle performance trade-offs, and finally, map out the future computing landscape. Let's jump right in. Section 1. Meet the microchip titans, the baseline of processors. Okay, to really understand the fierce modern rivalries shaping this industry, like the ARM-based Apple M3 going up against x86-based AMD Ryzen laptops, or AWS Graviton servers taking on Intel Xeon in the cloud, we first have to understand the ISA. That's the instruction set architecture. Think of the ISA as the vital bridge, or kind of like the master translator, between the software you run and the physical, tangible hardware of the computer. It defines everything about the hardware that the software can actually see and manipulate using basic machine instructions like registers and memory. It is literally the absolute foundation of how a computer computes. Now, you might be wondering, is the ISA actually different for different CPUs? Well, the short answer is absolutely yes. Different processors, like an ARM chip in your smartphone and an Intel chip in your desktop, implement completely different sets of instructions. They are literally speaking different machine languages. Section 2. RISC versus CISC architectures, the fundamental divide. Okay, let's dive right into the microarchitecture, because this is where the real magic happens. On the x86 side, we have what's called a CISC approach. That stands for Complex Instruction Set Computing. CISC is honestly a lot like a master chef who brings a single, highly complex gadget for every possible kitchen task. It relies on a much larger instruction set with really complicated instructions built directly into the hardware itself. These instructions vary in length and often take multiple clock cycles just to complete one action. Now, on the ARM side, we have RISC, or Reduced Instruction Set Computing. RISC is more like a chef who uses just a few simple, incredibly sharp knives to get everything done super fast. It relies on a small, highly optimized set of fixed format instructions. Generally speaking, RISC executes exactly one instruction per clock cycle, and memory access is handled by very specific, targeted commands. And this brilliantly illustrates what that looks like in the real world. Let's take a simple command, something like multiplying two variables. A equals A times B. For a RISC architecture like ARM, doing this takes several explicit, deliberate steps. You got to load variable A into a register, then load variable B, execute the actual product command, and finally store the result back into memory. It's 4 separate, simple instructions. But a CISC architecture like x86, it can often just use a single, massive complex multiplication command that handles the memory loading, the math, and the storing all in one single go through its complex hardware execution. So basically, CISC relies on heavy, complex hardware to do the work, while RISC relies on streamlined, optimized software. But here's the thing. ARM's massive advantage today isn't just about having a reduced instruction set. Modern ARM processors utilize what's known as a heterogeneous design, specifically configurations you might have heard of like big.little or dynamic queue. Instead of just slapping together a bunch of identical processing cores, ARM combines high-performance big cores for the heavy lifting with high-efficiency little cores for basic background tasks. It dynamically matches your workload to the absolute perfect core for the job. I mean, you wouldn't fire up a jet engine just to check your email, right? Add in the fact that ARM relies heavily on tightly packed system-on-chip or SoC designs, where the CPU, GPU, and memory are all bundled together, and you end up with a system that is just unbelievably responsive. Section 3. The energy efficiency revolution. Power meets precision. Before we look at the raw data, we need to understand a really critical concept here: energy proportionality. Simply put, this means a system consumes power in a way that is strictly linear to how much work it's actually doing. And here is why this is such a big deal. Typical data center servers usually operate at only 10 to 50% capacity. Traditional x86 processors have massive base power overheads. They draw a ton of energy even when they're literally just sitting there waiting for a task. They're absolutely not energy proportional, and that wastes a staggering amount of electricity. ARM, however, totally flips the script here. Under certain heavy database workloads, specifically online transaction processing, research actually shows that a server-grade ARM processor can consume up to 15 times less power than a high-performance x86 Xeon processor. 15 times. Because ARM uses simpler microarchitectural structures, it scales its power draw perfectly with whatever workload you throw at it. When it's not working hard, it's barely sipping power. And because of that massive reduction in idle power drain, ARM delivers up to 9 times higher overall energy efficiency. So even though the x86 chip might push slightly higher raw throughput at its absolute peak performance, the ARM chip achieves true energy proportionality. It's doing great work while saving an unbelievable amount of power. It's a real game changer.
Section 4. Performance and server battles. Trade-offs and triumphs.
Now, raw power isn't everything, but when we do push these titans to their absolute limits in the server room, what's really interesting here are ARM's specific performance triumphs. Take a look at memory bandwidth. The ARM-based AWS Graviton 4 processor pushes up to 120 gigabytes per second of memory throughput. That totally crushes typical x86 servers, which usually hover around 60 to 90. And why does this matter to us? Well, in AI workloads like large language models that are constantly shuffling massive data sets, this bandwidth difference gives ARM a staggering 168% advantage in real-world AI inference speeds. No way around it, that is huge. But hold on, do not count x86 out just yet. The heavyweight champion still flexes some serious muscle, especially in enterprise environments. x86 has incredibly optimized microarchitectural structures that have been refined over decades. If you have latency-critical, high fan-out workloads where your response times need to be perfectly predictable, x86 absolutely dominates. In fact, x86's tail latency, which is the absolute longest time it takes to respond to a request, is 2 to 11 times better than ARM. Throw in advanced features like hyperthreading and turbo boost to maximize peak throughput, plus unmatched legacy software compatibility, and x86 remains an absolute powerhouse. And honestly, that legacy compatibility is a massive defensive moat for x86. Just like this quote points out, if you try to run complex legacy x86 enterprise software on an ARM machine through emulation, you're going to take a 20 to 30% performance hit right out of the gate. Translating those complex CISC codes into simpler RISC instructions requires some serious heavy lifting. For performance-sensitive applications, native support is absolutely critical, which means a lot of big businesses simply cannot afford to leave x86 behind right now. All right, Section 5. The Future Computing Landscape, 2026 and beyond. So what's next? Well, ARM is taking its ultra-energy-efficient, RISC-based philosophy and literally expanding everywhere. I mean, it already totally dominates your smartphone and IoT devices, but now it's pushing aggressively into edge computing and micro data centers. Because ARM chips run so cool and draw so little power, you can actually pack them into small distributed servers physically closer to end users, which dramatically reduces latency. They are also being natively paired with AI and machine learning accelerators, driving this massive industry-wide paradigm shift toward cloud-native, energy-conscious computing. So the crucial point here is understanding the business reality of this whole shift. On one hand, the ARM ecosystem offers some incredible benefits. Fair and open licensing means cloud providers like Amazon can design custom, highly tailored silicon for specific workloads at a much lower initial investment. But the flip side is real. The strategic drawback is that these custom, heavily optimized ARM cloud chips create a huge risk of vendor lock-in. If your entire company's infrastructure is perfectly optimized for a proprietary ARM chip on one specific cloud provider, migrating away from them down the line becomes an incredibly difficult, expensive nightmare due to hardware fragmentation. Which leaves us with this final, truly vital question. Will the brute force and legacy power of x86 successfully adapt to this new, super energy-conscious era? Or will the agile finesse, hardware customization, and extreme efficiency of ARM fully conquer the computing world, from the phone in your pocket to the biggest servers on Earth? I'll let you ponder that one. Thank you so much for joining me on this explainer, and keep exploring.